get through like the 20,000 people in here yesterday to help us change reviews. And just like little things like that.
Is that on a Thursday?
Yeah. We thought hypothetically it would be good to, since we are used to being here at that time anyways, to come to the lab during the class time.
Oh, yeah.
And
Yeah,
yesterday,
Thursdays
like,
get
all
really,
hell broke loose
they get
during
really
the 2
hectic.
hours we were here. And then as soon as we were getting ready to leave, it was like the time that everybody else
Oh, really?
decided to go to.
Interesting.
So, where do you want us to turn these?
Just up in the front. Anywhere on that table, like by the blue power supply would be fine.
Oh, what happened? I took that 5. Yeah, because it's on the plate. I get here at 6:50 in the morning, so I leave my house at 6:30 because my class starts at 7. So it might, like, whatever happened must have been after. I leave, it's always backed up at about 39. Back. Like right past in between Maine and Fort Plain. Ooh. That's no bueno.
Yeah, traffic around here is kind of weird.
Yeah, I don't know what happened, but I-5 South is terrible.
Yeah.
Around 7:30 to 8.
I just got a car in January. I was biking for the first 2 years I was out here. So I'm discovering traffic patterns, and I teach over in Portland 2 days a week. So it's interesting.
When you commute from?
I live like 5 minutes from here, downtown Vancouver. Coming to park is easy,
Yeah.
assuming you get a parking spot.
Yeah, I commuted to Portland for a long time, last
Yeah.
few years. And jumping right at 14, which usually is alright, but because I pick up a coworker up north,
Yeah.
it's way worse.
Yeah. Yeah, it's somewhat predictable.
So this will sound really dumb, but when we were doing the lab, I was like so excited when I was like able to just like pick up a 2200 resistor without thinking about it.
Oh, cool.
Sweet.
Nice.
So just simple victories, I guess.
Yeah, that's what makes up life. That's awesome.
Just wanted to share for this morning.
I used to work for this think tank. They were affiliated with the Air Force. And some really challenging work I did there. And I had a nice office and it had a big plate glass window looking out on the lawn. And I used to sit there and watch the groundskeepers riding around on a mower, like cutting the grass. And I was like so envious. Because like they knew what they were going to do. They knew when they were done. They could step back and look at it and see it, and everybody else could appreciate it.
Instant gratification.
And I found out like a year later, my coworker in the next office, exact same fantasies.
What really brings to life the grass is always greener on the
Yeah,
other side.
seriously. All right, so recording again today. So it's my little anecdote is recorded. All right, any other lab 1s coming or lab 2s coming in? Had comments from a few people who, there's a stapler there. Had comments from a few people who can't be here or who didn't have the lab done. So for this time, so I said I'm taking off a point a day. I'm just going to take off 1 point for the weekend. So if you didn't get it in, and you get it in Monday, I'll just drop 1 point. Wow, where's everyone?
Well, apparently there's a lot of traffic on I-5.
Yeah. Okay.
So for people who ride the bus, and I know Vicky rides the bus, so she's probably
Okay.
really stuck in it, but I can text her and just
Any particular issues with the lab? Issues or comments or good lab?
it's cool to get to know the equipment.
Mm-hmm.
I think a lot of times, like especially for me, where I have no working knowledge of the equipment, I found that I spent the bulk of the time trying to figure out what I was actually supposed to do.
Yeah, yeah.
So, and then Thursdays from 9 to 11 are probably the worst possible time
Right.
to come in with what if questions.
Mm-hmm.
Just because there's a ton of people here.
Yeah.
But they were building really cool robots.
Oh, cool.
So it was like,
Yeah,
wow.
you can get a sneak peek of the other 120 class and see what they're doing because they start off with that as their first lab. So that's cool. All right. What I want to do today is go through an introductory view of Kirchhoff's voltage law and Kirchhoff's current law for solving complex circuits. And this is something we're going to come back to in a few weeks. So it's not going to be on the first midterm, which is coming up in 2 weeks. And let me toss the calendar up here. How many people have done the Chapter 3 quiz? Okay, I've got some comments from a few people. I think it's not due till May, but that's fine. So, we're going to finish up talking about analog circuits for now today, and on Monday we'll go back and we'll start looking at Chapter 1. Okay, so you should feel free to have read Chapter 1 by Monday. It's a quick read, it's just basic background engineering. What is engineering? What are engineers? Yeah, you can leave it right there, that's fine. So we're going to do Chapter 1 next week, and then Chapter 2 will begin the following week, and then we'll have a midterm on that Friday, so 2 weeks from today, which will cover what we've done in Chapter 4, what we've done in Chapter 1, and a little bit of Chapter 2. And then we'll go back to Chapter 4, and we'll do a full-blown discussion of KVL, KCL in detail. And your next 2 Chapter 4 homework assignments will be all KVL and KCL. But I want to give you an introduction to that topic today. We've alluded to it a few times. I just want to go through a little more detail. See where we're heading. Like the yardstick meter starting. So here's an arbitrary kind of horrible looking circuit. And we might be asked to figure out what the different voltages and currents are throughout this. And we can't really just combine resistors here. Even though this 7 and this 12 are kind of in parallel, if we try to combine these, we're stuck with what to do with this 10 volt power source. Same thing here, we have a 1 amp current source in the middle of these two. And these two we cannot combine in series because we've got something coming into the middle of them. So resistor simplification won't really help us in this case. So I'm going to show you a technique. This is Kirchhoff's voltage law. And KVL and KCL are essentially the same process. They're duals in this sense where we can go between current and resistance, current and voltage and parallel and series and so on. But by and large, most people find KVL a lot easier than KCL. I don't know why. I find KVL a lot easier. Even though they're basically the same process. It's like multiplication and division. One is harder than the other for some reason. So I want to talk about KVL first. So the idea of using KVL to analyze a circuit is basically we're going to draw some unknown currents in this circuit. We're going to call them loop currents. And we're going to use the fact that the sum of the voltages around a loop is equal to 0. And when we use this in combination with our loop currents and Ohm's law, of course, what we're going to get is a series of equations with unknown currents. So it's a little backwards. We're doing Kirchhoff's voltage law, but what we're trying to find are the currents in the circuit. Kirchhoff's current law we'll use to find unknown voltages in the circuit. And once you have one, you can find the other. But the direct result of KVL will be figuring out what the currents are. So a little bit of terminology. We can talk about things called meshes and loops. So here's a circuit. Really kind of sloppy. The details don't matter. So a loop in a circuit like this is any path starting at one point, going around some piece of the circuit and coming back to where you started without repeating yourself. So for example, if I start right here, this would be a loop. Okay, if I started right here, this would also be a loop. But if I come over here and I go up like in a figure 8 and I come down and come up here and across, that's not a loop because I've covered this resistor twice. So it's just what you think of as a simple loop. It can cross itself, it can't repeat itself. A mesh is a loop that's not contained in any other loops. It's a small loop, basically. So this would be a mesh. But this would not be a mesh. This is still a loop. But that's not a mesh. Sorry, a mesh is a loop that doesn't contain any other loops. So that's the smallest loop. So that's a loop because it starts and ends at the same point, but it contains two smaller loops, so it's not a mesh. So this rectangle is a mesh. This would be a mesh. So would this, and so would this. And those would be our only meshes, but there's more loops than that. Okay, so we're mainly going to be interested in mesh analysis. Does that make sense? All right, so here's how we apply KVL. First step, find your meshes. So how many meshes do we have in this circuit? Three, right? It's just this one, and this one. And we want to draw a mesh current inside each of these. So you can go in any direction you want, clockwise or counterclockwise. It doesn't have to be the same from one to one. I always go clockwise. So I'm just going to imagine a current flowing around here, and a current flowing around here, and a current flowing around here. And I'm just going to label these, and typically label them with uppercase I. I1, I2, I3. And here's the idea. We imagine that if the whole circuit was just this mesh, if all of this went away, we'd have a simple loop. It would be a 5-volt source, a 10 ohm, and a 5 ohm resistor with a fixed current I1 flowing around that loop. Yeah?
Does it matter that the 1 amp is flowing the other direction?
No. I mean, it will matter later on, but it doesn't affect. I'm free to draw this any direction I want. Now, if you know how to apply the technique, you probably draw I2 in the opposite direction, yeah, to match that.
So will the meshes in 1 and 2 both include that 5 resistors?
Yes.
Okay.
So to draw your mesh currents, just imagine these things sitting in isolation. So this second mesh is just a 1 amp source, 7 ohm, 5 ohm. I2 is going out with 1 amp. And I3, which looks like a 2. Battery and 2 resistors. The idea is when these meshes are actually sitting next to each other, the current flowing down here is still going to be just I1, but this resistor has two things causing current to flow. It has I1 flowing in this direction, and it has I2 flowing in that direction. And so we're going to have to combine those. Currents just add. Okay, you have a certain amount of flow in this direction and a certain amount of flow in this direction. You put them together, it's just the sum of that flow. Since these are going in opposite directions, the current going through, the current flowing down, for example, would be I1 minus I2 flowing in that direction. Does that make sense? Right? If it's just this part of it, I have I1 current flowing down. And since I2 is flowing in that direction, I also have negative I2 flowing in the opposite direction. So I can think of this as negative I2 flowing like that. So if we want to find how much current's going down, it's positive I1 and negative I2. It's just their sum.
Oh, going down.
Yeah. Okay, so find your meshes, draw a mesh current in each one. And then label your voltages. So, let me get rid of this. We don't know what the voltages on any of these resistors are yet, because we don't know any of the currents. So I'm just going to label these V1, V2, V3, V4. And we need to put pluses and minuses on them. And again, it's arbitrary which way we do it. It's going to affect how we write our equations later. But we can draw our plus and minus anywhere that we want. So I'm just going to go ahead and do what I usually do, which is put plus on the top and put plus on the left. So label your unknown voltages. And in this third step, I'm going to say write the KVL equations, which means use the fact that the sum of the voltages around any loop is equal to 0. And meshes are also loops, so if I say loop, it's the same thing. Just that not all loops are meshes. So we know how to add up voltages around a loop, right? We've been doing this since day one. Pick a direction. We've already got some directions drawn by our currents. Start at some point. If you go into the plus, add. If you go into the minus, subtract. So if we go around this first loop, and let's go in clockwise direction, so what do I get when I add up my voltages? What's the first voltage I encounter? V1. Am I going into the plus or the minus? Okay, so my first equation is positive V1, and then just going on that first loop, plus V2, and then
Minus 5 volts.
minus 5, and then I'm back to where I started, and KVL says if you go around a closed loop, the sum of the voltages is 0. All right, what about the second loop?
So that's not only V2.
So, okay, let's start. I'm going to start right here.
So you're minus
Minus
5.
Yeah, minus V2,
V2.
voltage.
Plus V3.
Current sources don't come into play here. Plus V3 equals 0. And I'm going to put this in parentheses, because we're actually not going to have to do that. But we'll leave that there for a moment. Let's do this third loop. So, I don't know, start down here.
Minus V3.
Minus V3 plus 10 plus V4 equals 0. Everybody see that? So we have 3 equations and we have 4 unknowns. And if I had 100 resistors along here, I'd have 104 unknowns with only 3 equations. You can't hope to solve that. If you had 3 equations with 3 unknowns, you can solve it algebraically. But since we have voltage sources in here, we may have a lot of unknowns. So we can't hope to solve these in terms of E. But if we can replace this with equations involving I1, I2, and I3, we'll have 3 equations and 3 unknowns. Just our 3 loop currents. So our fourth step is to rewrite our equations with I instead of V. I instead of V's. So our first equation was V1 plus V2 minus 5 equals 0. Can we rewrite V1 in terms of current somehow?
Yeah.
More than that.
10
Yeah, so we can use our favorite equation, V equals IR. So on that 10 ohm resistor, our voltage is V1, our current is I1, and our resistance is 10. So we can write V1 equals I1 times 10, or just 10I1. All right, what about V2? So this 5 ohm resistor. So what's V? It's just V2, right? And what's the current? I erased it, but we said it a little while ago. And minus I2. So the current going into the positive side here is positive I1. But the current going to the positive side from this loop is negative I2. So we have to take their sum. I1 plus negative I2 times the resistance, which is 5 ohms. Right, this is V1, this is V2, minus 5 equals 0. This is the whole trick, writing these equations. But all you have to do is methodically apply Ohm's law to each unknown voltage source in your circuit. So if it's sitting alone on a piece of your loop that's not shared with anything else, it's just going to be your loop current times your resistance equals that voltage. If it's sitting somewhere here where there's two or more loop currents contributing to it, you have to add them together. And you have to be really careful how you add them, whether you add or subtract, plus or minus. So you've got to look at the current flowing into the positive, and you've got to make sure that if this is going to the negative, you look at the negative current going into the plus, and you add them together. Okay, this is why we've been talking about how to add voltages around loops, and specifically so we can do this.
So for the V3 would be plus I2 minus I3.
Sure, V3 would be the current flowing into the positive, which is I2, plus the current from this loop flowing into the positive, which is negative I3. So I2 minus I3 times the resistance. And what about V4?
That's the yeah.
So it better be something times something. So V on the left is just V4, right? That's what we're trying to find. What's the current flowing through that resistor? What's the resistance of that resistor? That's all there is to it. Okay, there's a voltage source sitting up there. We don't have to worry about that yet. All we need to know is the voltage across this resistor, and it's always going to be the current flowing into the plus, which is I3 times the resistance 12. And we can have 100 batteries before and after that, and it doesn't change the voltage across that resistor. It's still 12I3. Alright, so let me just algebraically clean this first equation up a little bit. This is going to be 10I1 plus 5I1 is going to be 15I1. And this is going to be negative 5I2. And I'm going to bring this negative 5 over here and just say that's equal to 5. So that's going to be one of our equations. And I can divide it by 5 and get 3I1 minus I2 equals 1. But I'll just leave it like that. So that's one equation. All right, let's add up the voltages around that third loop. This was the equation we had. And we just found equivalent ways to express V3 and V4 in terms of our currents. So we can take these and this and combine them to get a new equation. So negative V3 is going to be negative I2 minus I3 times 7. Everyone agree with that? All right, plus 10. Plus V4 is just 12 times I3. And that's equal to 0. All right, so we can clean this one up. That's going to be negative 7I2 This is going to be negative I3 is positive I3, 7I3 plus 12I3 is plus 19I3. And that's going to be equal to negative 10.
So what is happening?
I just algebraically simplified this. So negative I2 minus I3 is the same as negative I2 plus I3 times 7 plus 10 plus 12I3.
Why is that negative in front?
This one?
Yeah.
Oh, because our equation was negative V3 plus 10 plus V4. So this is V3, so I just threw a negative sign in front. If you get the wrong answer, that's why it will be.
Oh, no, I thought you were doing the second one. That's
Okay. No, doing the third. But yeah, this is where all the mistakes happen. Okay, is trying to combine these things because the pluses and the minuses are critical, and particularly after like 3 hours of KVL, KCL homework, it starts to all look kind of the same. All right, so there's the second equation, and so now we've got two equations, and we've got three unknowns, I1, I2, I3. Now normally what we would do is we would do the same thing for this loop. We would write another equation, we would substitute in the expressions for the voltage, and we come up with a third equation in perhaps three unknowns. But because we have a current source, we can do something, right? We can look at this and we can know immediately what I2 is equal to, because with a current source, the current is the same everywhere around the loop. Oh, with any loop, the current's the same. But since we know we have 1 amp up here, we know that this entire loop has 1 amp going around in this direction. So we have 1 amp in this direction. That means we have negative 1 amp going in the direction of I2. So we can immediately say I2 is equal to negative 1. So when you're doing KVL, because our goal is to find the unknown currents, if you have a current source sitting in a loop, you can immediately write down what that loop current is. So we don't actually need to sum the voltages. And in fact, you can't because you don't know if there's a voltage drop across that. But we don't need to. We can look at this one and you can immediately say I2 equals negative 1. And that's our third mesh equation. And now we have three equations and three unknowns. Our three unknowns being I1, I2, and I3. We've got 1, 2, 3 equations. And we can solve those and find what each of the currents are. Does that make sense?
I just plug in I2.
Yeah, so the easiest way, we've already got a number for I2, so we can plug that into here and here. So this equation will be 15I1 minus 5 times negative 1 is just positive 5 equals 5. Well, that's kind of weird.
That is kind of weird.
Yeah,
0.
cool. That would freak me out on a test. I'd like spend my whole time trying to figure out what I did wrong, so I won't give you any of those. But assuming we didn't make a math error, that's what I1 turns out to be. And then this equation, negative 7 times negative 1, this becomes 7 plus 19I3 equals negative 10. 19I3 equals negative 17. I3 equals negative 17, 19, 7 amp. And what's happening is just by pure chance, the way I set these resistors up, the current coming out of here is counteracted basically by the fact that we have a current source and perhaps a voltage source in those other loops. So this current is 0, this is 1 amp flowing in counterclockwise direction, and this is 17, 19, 7 amp flowing in that direction.
You got a 0 and you got a prime fraction.
Yeah, that's kind of cool.
That's unfortunate.
All right, that's the basic procedure. And like I said, we're going to come back to this. We're going to spend another week on it in a few weeks. But the idea, the step-by-step description of how you do this is very straightforward. Okay? breaking down that wall by hitting my head against it would also be really straightforward, but it wouldn't necessarily be easy. So when I say this is straightforward, I'm not saying it's easy. You can sit down and bang it out in 2 minutes. But the goal will be to make sure that moving from one step to the next is something you can do. And that given enough time and patience, you could go through and you could analyze a circuit like this by following these steps. Questions? And as I've mentioned to a few people recently, and I mention this every quarter, a lot of the stuff that we do in this chapter will have the following effect on most people. I can go through a problem and I can solve it, and every step makes sense. And you can say, sure, if this is our equation, then V3 is equal to this, and V4 is this. And there's no question that comes up when you're actually watching it being done. But then if you take a problem and you try to do it, it looks like nothing you've ever seen before. Okay? And every physics class I ever took as an undergrad was that way. I'd go to the session, I'd watch all the problems worked out, it made perfect sense, then I get the problem and it was like, what the heck am I supposed to do with this? And that's natural. And the only way you get through it is just by hitting your head against it. Just taking the problems and working them as far as you possibly can. Take a break, come back to it. When you can't push it any further, right, ask for help. Find someone to work with, or shoot me a note, or Google it or something. And eventually it will click. But your individual brain has to make these connections and get these pathways wired in a way that makes sense for you. And I can show you the technique, but I can't actually teach you how to do it yourself. Okay, that's just an experience thing. It's like driving or painting or anything else. It just comes with practice and experience. So like I say, the next two homeworks in chapter 4, which won't be due until several weeks out, are just a bunch of KVL, KCL problems. And they can definitely be frustrating. But it's a practice thing. May as well go ahead and do KCL. Just to put it in your brains. And like I say, in some sense, it's basically the same thing, but it feels very different usually. So KVL, Kirchhoff's voltage law, we were looking at loop currents. In KCL, we're going to look at something called node voltages. So KVL is loop analysis, or mesh analysis. KCL is node analysis. So a node is a place where 3 or more pieces of your circuit come together. So, for example, this is a node. We can call it N1. This is a node N2. Are there any other nodes?
So N1 would be the whole thing?
It's a point. It's this point right here where those 3 resistors come together.
N3.
So this would also be a node. This would also be a node.
So where the 3-point max?
3 or more things come together, that's a node. This is technically not a node because it's really just a resistor and a piece of wire coming together. It's just part of the resistor. But actually, this point here is a resistor and two pieces of wire coming together. So is that really a node? It kind of depends on your definitions. Look, one way to think about a circuit like this is if you redraw it. That's exactly the same circuit, right? This is my 5, 6, 10, 3, 3. It's the same circuit electrically, right? So if you draw it like this all looks like just one big node where you've got four things coming together actually. So when you do an analysis like this, each node is going to generate an equation. Okay, so fewer nodes would be better. So actually the way to think about this is all one big node. And if you don't do that, if you treat them as separate nodes, you can still solve it, but you end up with 4 equations instead of 3, and it's more work.
So, for an example, if there was no resistor on the top, would that make it one node also instead of one and two?
If this wasn't here?
Yeah.
Yeah. Because if you don't have this resistor, if that's just a wire, I could actually redraw it as I could just redraw it like that.
So there's no one.
So that would just be one node at the top. So you want to try to bunch them together. So in my first class I did this and they called this the banana thing. So I take all these and you bunch them together. Alright, that's...
Then in that situation, would
That's
you be
not
able
the
to
same
have them in parallels?
Yes, except when you do KVL, KCL for homeworks or exams, it usually says do not simplify. Okay, but yeah, if you just wanted to get the answer, you can combine these, and combine that, and combine that, and combine that, and be done. Alright, so we're trying to find these unknown node voltages. And voltage is a funny thing about them. Currents are just absolute currents. If I draw a current around here, I can actually measure what the rate of flow of electrons is. I can figure out how many amps I have around this loop. It's unambiguous. When you talk about the voltage at a point in a circuit, you've got to say what it's relative to. Because voltage is a difference in pressure between 2 points, a difference in potential between 2 points. So talking about the voltage at this point is meaningless unless we have some reference that we're measuring relative to. And usually we take our reference to be some ground, but we might have a bunch of batteries in here. There's no one universal ground point, but you have to pick some reference point. So in KCL, so label your nodes. We get to pick one of our nodes to be a reference. And we get to arbitrarily say that that's going to be 0 volts. Because voltage is all relative. Right, our 1 amp flowing through here, that's absolute. Right, it's just 1 amp. It's a certain number of electrons flowing per second. 10 to the 24th, whatever the number was, 10 to the 18th. But if I say, what's the voltage at this point? That's kind of an open-ended question. If I ask, what's the voltage at this point relative to this point, that's 10 volts. Or if I ask, what's the voltage across this resistor at this point relative to this, that's 10 volts. But if I just say, what's the voltage here, there's no basis for answering that. And in fact, I can build a piece of circuit over here with a 10-volt battery, and I could build another circuit over here. And maybe I plug this one into the wall to power it. And if I measure the voltage between here and here, it might be 100 volts. It might be pretty close to the same, it might be a few volts, it might be 1,000 volts. There's no inherent notion of the voltage at a point. It's always relative to something. Now, if I have some common point, if I measure the voltage of here relative to, well, I'll come back to that. All right, so voltage is always relative to something, which is why we can pick a base node and just say we're going to assume N3 is 0 volts. But this might be at 100 volts higher potential than this point. So when you have a power supply like these, it's got 3 plugs. The left one says minus, the right one says plus, and those are the 2 places where you take your power from to drive your circuit. But this middle one is labeled ground and it's green. And when you have a 3-prong plug, that middle prong, that's ground. And that goes into a part of the outlet which is connected internally to something that should be at a common voltage to everything else that's plugged into that middle prong. So the whole reason we have 3-prong plugs is to try to give us a common sense of what ground is, a common base potential. And anything you plug in with a 3-prong outlet, that middle pin that goes into there is going to be at the same potential as any other piece of equipment you plug in somewhere else on the same circuit. And theoretically, all these grounds are at the same potential, and the base we use for the potential is earth, ground. So this symbol used to actually be called earth, and now it's usually just called ground. But if you have 2 pieces of equipment with 2-prong plugs, and you plug them in, the voltage at some piece here in this circuit might be very different from the voltage of this piece. And that can be a problem. So a lot of times you get your guitar out and somebody cut the 3rd prong off of the amplifier plug because one day they didn't have a 3-prong outlet. And now the potential voltages in your amplifier and your circuit, which includes your guitar, are floating. They might be anything relative to something else. While you're sitting on a chair, you're connected to the earth, you're at a ground potential that may be very different from the ground potential of this amplifier. And you touch your strings and you get a shock. Or you start sweating and your resistance goes down, you touch your strings and you get a shock. And it's a grounding problem. So, alright, so that's a sidetrack, but it's a good thing to talk about. Just don't cut the 3rd prong off of your equipment. Alright, so KCL, we're going to pick a reference and we're going to set that equal to 0. So I'm just going to arbitrarily say this equals 0. And I could just decide N3 is 1,000,000 volts and I can still solve this circuit. And if this is at 10 volts relative to here, when I'm done, I'll find N1 is 1,010,000. You still get the same answer, but it's obviously going to be easier if you work with 0 than 1,000,000. So we set our ground potential equal to 0. And we're not going to finish this up today, but basically what we're going to do is we're going to look at currents flowing in and out of these nodes. So we're going to draw these currents, I1, and again, these can go in any direction you want. But we're just going to look at what's going into and out of each node. And so now we're going to write node equations that basically say the sum of the currents going in and out of a node is equal to 0. So KVL, our equation said the sum of the voltage around a loop equals 0. KCL, we're going to say the sum of the current going into a node is equal to 0.
What's the thing in front of I again?
That's a summation. I'm just the shorthand for the sum of the currents.
Oh, okay.
there a reason you're using small I?
Yeah, because we actually mean an individual current along this branch. Whereas in KVL, we're meaning like a loop current, taking that and that loop in isolation. It's just kind of what people do. All right, so let's just do the KCL equations at these nodes, and we'll call it a day. So at node N1, we have I1. We can add up the currents going in or the currents coming out. Let's do the currents going in. So the currents flowing into this node, we have 3 branches. So we have I1 flowing along the 3 ohm resistor. So that's positive I1. We have I2 flowing out of that node, which means we have negative I2 flowing into it from this direction. And similarly, we have negative I3 flowing into it from this direction. So if we add up the currents flowing in, I1 minus I2 minus I3 equals 0. And here we have minus I5 flowing in, minus I4, and positive I3. So at node 2, I3 minus I4 minus I5 equals 0. Same situation as before. We have 2 equations, but we have 5 unknowns here. We can't solve those. But if we rewrite our currents in terms of N1 and N2, we're going to end up with 2 equations with 2 unknowns, N1 and N2. So our last step is rewrite I's in terms.
Are we just gonna ignore the bottom one for now? Or
We already know what this voltage is because we've just decided it's going to be 0 volts.
Okay.
So we're not going to have to solve for that one. But again, if you don't, you end up with more equations and you can end up solving for it. And you end up with an underspecified system. You'll end up with 3 equations in 4 unknowns, and you get to pick one of them for 3. Or 2 and 3. So all we need to do is replace these i's with something involving our n's, and we can do that with Ohm's law. For example, we know the voltage between here and here is going to be 10 times I3. So eventually we would just take this, we would rewrite it, and we'd end up with 2 equations with the unknowns N1 and N2. We solve those, we've got our voltages, and then we can plug those in and get our currents. That's in 2 weeks. Okay, that's just a preview. Monday we're going to start in on chapter 1. We'll talk about engineering and all things related to being an engineer. All right, have a good weekend. I'll see you next week. Yes, if you have your lab 1 or lab 2s, turn them in up here at the front. Rewrite in terms of the ends. Rewrite the i's in terms of the ends. Week from today. Yeah, it's due on Monday. 1 to 4. Yeah, no, just 1 through 4. Yeah.
And you want that handwritten or?
Yeah, just turn it in on paper. So handwritten or computer, up to you. I recommend hand. All right, thank you.
And I have a question.
Yeah.
So yesterday I was about to temporarily lunch.
Mm-hmm.
And then I switched on the lights and the 6 light bulbs and the radio started to get fuzzy. Is that what the magnetic thing that you were talking about?
Most likely.
Alright, thanks.
Cool. Yeah. Chapter 4 homework questions 1 through 4 are due on Monday. And there's an online quiz that I think is due Monday also. I think so.
Yeah.
The first quiz?
What's Monday?
Oh, it's Monday?
Yeah.